So this is where we stopped last time, and yeah, what I was just saying, I wanna make a joke, but yeah,
we can get more.
Okay, great. So, but just to pave the road a little bit so that the details will be structured properly, I wanna say that in general, what's the main idea here is that we would like to have a parameterization for unitary, because that's something that we will be using in the VQE in general to some unitary. And so what's the form of unitary that will allow us to obtain any state in this large Hilbert space of all the qubits, right? And before going and doing this, I guess, search for this unitary, it's nice to have some sort of form what this unitary should look like. And one way to do it is recognizing, okay, we're working in this n-qubit space, and general unitary will be a part of SU 2 to the n group. And the form of that unitary will be product of some angles with some generators, and these generators they need to be anti-Hermitian, as we were discussing, so that the form giving us unitary. And one simple kind of approach for this, one simple choice for these generators is just to be, so they need to have I and then Pauli product. Okay, so these Pauli products, there is they could form the generators if you multiply them by I, right? And then there will be 4 to the n minus 1 of them minus 1, because generally we have these Pauli products that can contain any product of sigmas for different qubits, right? And we said that this sigmas could be 4 possibilities. One is identity, and 3 others are Pauli products, Pauli matrices X, Y, Z, right? So if all of them are identities, that's unity, and then it's not really necessary for this form, right? To have well, the full identity would be just a constant factor, which won't do much, right? So, and this is kind of a general form for the valid unitary transformation. It has a disadvantage, of course, is that we are in a big space and the group is large. I mean that the number of generators is exponential. And so hopefully this will not be needed in the practical calculations, but it's nice to have form, the exact form, like in the classical simulations. We know that in order to solve n-body problem and electron problem, we could do full CI always in the finite basis, and that's the exact answer in that finite basis. So here the same. This is the exact answer if you take the exponentially many Pauli products, and this is one way to build this unitary. So all this discussion now about UCC, disentangled UCC, is about alternative form of potentially exact unitary coming from the sort of fermionic intuition regarding that we could maybe unitarize the couple cluster theory, right? And make it in this disentangled form where it's a product of some amplitudes, essentially the same form, but now these generators, they are coming from the fermionic, let's put them in this way. So they can always be written as a product of some excitations, PQ. For the excitations, we don't need P and Q be the same. It could be always different. And minus Hermite conjugated part, which is QP, right? So we could have multiple products like this, and this will be like our our generators essentially, right? And so we could take the if there is only a single product, then it's a single excitations, then two products are involved here, so doubles and so on and so forth, right? So this is the disentangled UCC sort of hierarchy of unitaries, and here there is we discussed that, of course, depending on the order of these unitaries, we will have potentially different results. At the single and double level, we saw like this work actually was showing that the discrepancy, like generally the accuracy could be quite different if you optimize all the amplitudes with respect to energy. Still, the kind of the final results could be very different depending on the order. And but then that's not the worst case actually scenario, because okay, the results are different because we don't have the entire set, but it turns out that there are more difficulties here with this form, and that was found in this paper cited here, 2019, where there was a very insightful analysis done where we looked at the kind of just a 2 electrons, 2 orbital system with, you could think of it as a like a hydrogen molecule in a minimal basis set sort of a problem, right? So we know that any wave function in that subspace of 2 electrons with 2 orbitals can be written as a linear combination of 4 Slater determinants. Here, the notation is I is like, yeah, essentially the index corresponding to occupied, but there's only one occupied, so I could be thought as 1, and A could be thought as 2, right? So, but just following the usual notation that occupieds are IJK and the A and BC are virtual. So this is the reason they use this. And then the bar on top is just the, or absence of the bar corresponds to either we have alpha spin or beta spin, right? So we start with Slater determinant, like a Hartree-Fock one, double occupied on the I, and then some other four determinants, right? And then if this is a very simple system, which allows us to say, all right, all we really need to think of here is 2 types of excitations written with this kappas. I guess the kappas is this actually in this form because it has a lower subscript and upper superscript. So essentially, if you have just the one pair, that's excitation de-excitation, and if there are 2 indices, that corresponds to just the doubles, right? So we have 2 single excitations and 1 double excitation in this system from the, say, if we consider our initial state is occupied II, right? Then we could doubly excite, or we could excite first I alpha spin to the A or beta spin. That's it. So there are only 3 operators, only 3 generators. And technically, we would think that any state should be able, or if this parameterization is correct, then any state could be generated using any order of these generators, really, or unitaries, elementary unitaries, acting on the of some kind of arbitrary chosen convenient state. In this case, it's our Slater, Hartree-Fock Slater determinant, let's say. But it turns out, in this work, it was found that if you take the, say, superposition of the middle 2 configurations, right, with equal weights, right, then it turns out that you could go ahead and try to optimize the amplitudes. Here they are denoted T1, T2, T3, right? So you could try to optimize these T's so that essentially whatever you get with the fixed T1, T2, T3, that should have 100% overlap with this state that you are trying to find. And that is possible when you put one single, then double, then another single. And that is not possible if you put two single excitations first and then double excitation after. Okay. So it turns out that there is an order dependence, and essentially not every order allows you to generate arbitrary unitary, right? Because we're talking here about the states, but you could also reformulate the problem that you have a specific unitary that acts on I with a bar, and you wanna, if the unitary that is parameterized properly, then you should be able to obtain any state you want. And the state they want is this one. And it turns out with one order, it doesn't work, right? So that means simply that order doesn't allow you to generate every unitary if you just optimize the generators, or amplitudes of the generators. And in order to understand this, in this paper, essentially, we're stating the problem that this disentangled couple cluster theory does not provide the exact parameterization, okay? And we decided to understand in my group what's going on there. And in order to kind of clearly see this, what's the problem, what's wrong with this set, essentially, I need to first introduce a few things, a few facts, essentially, we know about, sorry, not Clifford, but Lie groups, Lie algebras, right? Because essentially, we are trying to parameterize Lie group element, or that is a general Lie group element, using potentially Lie algebra operators that are generators for the Lie group. Okay, and so this is a formal definition of Lie algebras we informally discussed, right? So it's really, I wanted to put it here so that you have a kind of rigorous definition somewhere. And but the idea is, as we were already discussing, if you have a linear space of objects, linear space meaning that you can have these operators as like thinking of them as like abstract vectors. You can multiply them by some. You can multiply them by some constants, and you could add them. The constants are from the sum field, real numbers, complex numbers. You could, for generality, always think as a complex numbers, right? And then you have this, and what you get is still an element of the field, or sorry, not the field, but linear space, right? But on top of that, we're adding an additional binary operation, which allows us to essentially multiply our vectors. And in this case, for the operators at least, that multiplication is defined as a commutator, right? But in general, it doesn't need to be commutator. In this abstract sense, it's just some binary operation that gives back some element again from our linear space. And every element in the linear space can be written as a, of course, linear combination of bases. Let's say in linear space, you could always find some basis, right? And then that basis could be used to express any element of the space, right? Now, as I said, it doesn't need to be commutator. It's generally at the abstract level is just some binary operation that satisfy the following conditions. By linearity, so as you could see here, x plus y could be then if you do the same as with commutator, right? So if you do the commutator of the sum of operations with the third operator, then you could break it. And so all the natural things, Jacobi identity we talked about as a kind of substitute for associativity, which is not present in this kind of version of the product. And also we have kind of antisymmetric condition that if you change the order, then you get the minus sign. Right, so this is effectively the definition of Lie algebra. And these Lie algebras are useful because they allow you to study Lie groups, and the Lie groups clearly is something that we want to understand better because our unitaries in VQE is coming, they are coming from the Lie group. And so then Lie algebra essentially have this nice closure, meaning that if you take the objects of the Lie algebra set, Pauli products, for example, do the commutators, you get back linear combination of the same objects. They stay in the algebra. Now, turns out that the Lie group can always be presented as a essentially product of these exponential functions. And well, no matter, I guess, if you multiply the different u with different amplitudes, taus, you will get back, again, element of the group. And you can always represent the element of the group as, again, a single product of all the generators, right? So you could nicely do u tau 1 vector times u tau 2 vector, and you always write it as a u tau 3 vector, which will be a product of all the, let's say, if we're working with Pauli products, then these are all the, I guess, 3k pk product of the k, right? So there's a disclosure as long as we have all the generators of the algebra that we use. Okay, so this is a nice property. And also another nice feature is that essentially we could represent, there are different parameterizations. One is like this, a product parameterization. Another parameterization of Lie group could be written as a single exponential function with the sum of all the tau elements, let's say tau k f pk, right? So this general element, because what we have here is exponentiation of like element of the algebra. This is like our generator, and the exponentiation of this general element of the algebra will give you element of the Lie group. Okay, and you could show. Unfortunately, I don't have a very simple way to show this, but there is a way to show in mathematical literature that you could change the order of these exponential functions in the product, and still will be able to recover a particular element of a Lie group. For that, even though, like, if you change the order, then the amplitudes could be different in the case of different orders, but you still will be able to recover a particular element just by changing the amplitudes. That's a nice property. But of course, for that, in order to have that property, you want all the generators from the algebra. You cannot skip things. This is this example where if you have P1, P2, and the commutation requires to include the P3 in the Lie algebra, then the generally exponential function of the sum cannot be written as just the product of two exponential functions. You need P3 here, but the order doesn't really matter. Okay, so you could adjust to a particular order, and there is a generally way to, if you have coefficients here, you could obtain these coefficients using some procedures that yes, we may talk later about. Okay, but this is the sort of the framework that is known. And now, if well, starting from that, we could sort of see that probably the bottom line of the order problem, in the case that was discussed before, like this case where some orders don't really give you the full representation of the group, they are really coming probably from the fact that these generators that were used there, they are not forming the Lie algebra. right? So this is the suspicion that we got after kind of realizing, okay, well, these are known mathematical facts, and indeed, yeah. So we will, yes, we will confirm that in a moment. But before we go into back to the original problem, want to say that okay, if you now want to maybe do the exact parameterization of Lie group using the full Lie algebras, in these situations, there is a usually exponential blow up if you, of the terms if you try to close the terms of the from the some set of generators that you start with, and in the case of fermionic algebras, we could think of essentially starting with linear, like one electron generators, and adding the two electron ones that actually is, as we'll see, enough to bring, if you start making the commutation relations between the two, you will be able to generate the 3 electron excitations, 4 electron excitations, so on. So, and eventually you get exponential blow up of terms, so you will get to something similar to 4 to the n minus 1, but in the fermionic space. And one way to somewhat mitigate this issue in general is that in the Hamiltonian problems, we have also symmetries. So symmetries could allow you to reduce the number of generators in the algebra, turns out. So how is it working is that you could, it essentially works in the following way. So if you have some symmetries, there is this nice property that is coming from Jacobi identity for any well, commutator related expression, commutators satisfying Jacobi identity. And what's happening here is that if you decided, okay, I will work with some generators, Pi and Pj, and they are both commute with some symmetry set, right? So then, since the commutator here is 0, commutator here is 0, so these two terms are 0. And what is nice about that is that then overall expression is 0 according to Jacobi identity. So then that shows that actually the commutator of these two terms of two generators that you decided to work with, it's also going to be commuting with the symmetries, right? So a simple example of that would be if these guys commute with the number of electrons, and these guys commute with the number of electrons. So then commutator of these two will also commute with the number of electrons. So you cannot break symmetries by creating more and more generators, but generally you could reduce the number of terms if you start with symmetry adapted generators, right? So that's somewhat a way to reduce the number of generators that one would need to consider in the set, right? If you know that we're interested only in maybe subset of unitaries that preserve the symmetry, work in, say, singlet space. Now, of course, you would want to start then with the generators that preserve symmetries as well, okay? All right, so returning back to this example, turns out that if you check by start making the commutators of this single and double excitations, right? So this, by the way, is in this notation would be kappa PQ, and then, sorry, QP, excitation to P, right? And this one would be kappa QS PR, right? So it turns out that this set is not a Lie algebra, which is a little bit surprising because what else is there, right? So if you kind of generally, if you look at what's happening when you do these commutators of the fermionic excitations, you're going to get out of the single excitations, you're going to get the single excitations back. it turns out that this set is forming the closed subalgebra of the general algebra. But once you start including doubles, then doubles with doubles give you triples and so on and so forth. So it's a easy algebraic exercise to show, right? And so, but we don't have anything. We have only 2 electrons, and any triplets would be sort of not relevant in this case. But yet, turns out if you do these commutators, here's what you get. This could be shown again with a brute force, just commutation exercise, commutation evaluations, right? And so what you could see here is on top of the excitations and de-excitations, which are in the kappa operators, we also start getting the occupation number operator and P, which is a dagger P, AP, right? And so there are these occupation operators that pop up here and there. But this is this algebra of 8 elements in total. And then you could kind of massage this a little bit by splitting it to the so-called center, which is the subset that commutes with everything. And then the 2 subalgebras, which are equivalent to SU2. So this is just trying to analyze what is the structure of this thing that we obtained, the set we obtained. So by subalgebras, what I mean is that if you do the commutation of these 3, they are like having a sigma x, sigma y, and sigma z, right? So they will go into each other, right? So like sigma x, sigma y will give you sigma z, sigma x with sigma z will give you sigma y. So they are closed separately with respect to the commutations, but in general, they are not commuting. Like elements from here will not commute with elements from here. It's just that if you do the commutations of this subset, you will not get elements of this subset. But if you start doing the cross commutators, they will be able to produce something else. So that's kind of just some structural aspects of this. And what we decided to do further is to kind of use the symmetries, because 8 elements, so 8 elements in this set is a lot. So we were trying to figure out kind of a simpler consideration of the problem. And when we include the number of electrons as z and s squared, which we know, then for this problem, we found only 4 elements that commute with all the symmetries and form the closed algebra, where again, one of these elements, again, we could write as like a fully commuting operator with everything. And that usually doesn't produce anything in sort of a state. It's just actually phase factor. But what is left is these 3 elements, which are turns out to be isomorphic or equivalent to essentially SO3 or SU2 again. SO3 algebra, it's another name for SU2. So they are kind of, there is a 1-to-1 correspondence which can be made. And so these 3 elements, 2, 3, and 4 in this notation, they are forming the closed set that commutes with these symmetry operators, right? And it turns out that then if you use this set, you could put any order, and you always can find amplitudes for any order that will take these states and generate essentially the state that they were interested in, okay? So the simple, I guess, conclusion here is that disentangled couple cluster theory has problems with, this parameterization is problematic because the generators that are only excitations minus de-excitations, they don't form the kind of closed Lie algebra. Okay, but if you do the closure, you could add the symmetries if you want. You could ignore symmetries. Just without symmetries, it like in this case, we had 8 elements without symmetry, but if we add symmetry, we could reduce it to 3 elements, right? So symmetries don't fully prevent the exponential blowup usually, but in many body problems, but they reduce somewhat a prefactor, okay? And so that's what happened here. We could restore the order independence in this case by just closing the algebra.
It's like conceptually, is it similar to like working with configuration state functions in CI expansions instead of determinants directly? That you
So that's a symmetry versus non-symmetry, right? That's that would be conceptually similar, right? But if you have not, if you don't have all the determinants, then you won't be able to represent any state in the Hilbert space. So that's the kind of analog of the effects that we saw, because what they used is the generators that were not spanning the entire Lie algebra, right? Entire space. Yeah. Okay. So that was the origin of the problem. Okay, so now here I wanted to say a few words about the kind of fermionic algebras that are available in general. And unfortunately, there are not so many. So we could actually, I already said that kind of single particle excitations, they form a Lie algebra that we could use for the orbital rotations. So in Hartree-Fock method, for example, we have all the unitaries that are involving this product of essentially exponential functions of the A dagger P, AQ minus gamete conjugated version with some amplitude PQ, here P on Q. Right, so this is a general form for mean field rotation, and it is it's order independent, meaning that you could put it in any order. You would just need to adjust the amplitudes. The reason for that is that these elements they form, or for like in short, we could usually sometimes they are called the excitations E's, right? And then the closure relation that one can actually easily check using the fact that we know the anti-commutation relations for A and A dagger, right? So turns out that if you do this kind of commutators, then the result is another set of E's. So the first one is, let's say, PS with QR, delta Kronecker, and then another one is RQ with PS. Okay. So because, as you can see, the E's, when they commute, they produce a linear combination of other E's, and therefore we have a Lie algebra since this is the condition that is needed for Lie algebra. Now, the problem starts when we go to the, say, doubles, because you could easily see that if you take the double E and take another double E, so then what's going to happen is you're going to lose one, like essentially the commutator is a product of E's minus another product of E's. And as you can see, you lose one E by doing that because of this relation. And you could check me. Essentially, in this case, you have 4 E's in the commutator and you will lose one only. You will get triple E's, right? So this is like very simple hand wavy kind of way of showing that, as you can see, that the double E's, they don't form Lie algebra because they will produce triple excitations and so on. So triple excitations together will give you pentuple excitations because, again, 3 plus 3 is 6 minus 1 that you lose because of the commutation and so on. So let's start sort of growing. All right, and therefore the only really two Lie algebras that we could get out of the fermionic excitations is either the entire exponentially many entire kind of set that is equivalent to Pauli products. It's just written in the fermionic space, and then it's bigger than what disentangled couple-cluster theory produces, because disentangled couple-cluster theory just uses these particular operators. So if you do the commutators, there will be others in order to complete the algebra. But it's both like disentangled couple-cluster theory, and the entire thing is exponentially large, essentially. Right? And then there is this mean field rotation Lie algebra that kind of has only n2. If we have again n orbitals, then the number of the elements is n plus 1. Actually, it's n squared in general, n square elements, and then there are some. If we just account for the ones that they go into the rotations without occupation numbers, then we get n times n minus 1 divided by 2. That's enough to do the rotations. And yeah, so it's a polynomial in size of generators that we need. Okay. All right, yeah, so that's essentially what I was saying, that the singles with singles give you, again, singles, that's why it's closed, but doubles with doubles give you triple, and then in general, it's n tuple with n tuple give you n plus n minus 1. And then before we get to the next point, actually, there is an interesting thing that we'll be using later, is that if you have singles and doubles, that's enough. If you do all the commutators and the commutators of what will come out, you will be able to generate the entire set, of course, right? So that's why singles by themselves is not enough. But if you have singles and doubles and do all sorts of commutators, then you could generate the whole set. Okay, so yeah, so some of this fermionic rotation, if you wanna do the symmetry conserved generators, then you need to do the linear combinations. For example, for singles, in order to commute with S squared, we need not only excite the alphas and betas, but bring them together to a generator. And then, yeah, general fermionic rotation provide Pauli products. And then, interestingly, one can show that all the Pauli products inside one fermionic rotation, they actually all commute. So if one would need to exponentiate the fermionic generator, then there is no problem of exponentiating individual Pauli products essentially inside the. But if someone needs to do the IA, right? So then this will be equivalent to Pauli excitation, essentially product of exponential functions of the Pauli products that are inside the K. And the order again could be different, could be any, because all these Paulis, they commute with each other, right? So it's not obvious, but one can show that this is the case. And it's independent whether it's a single excitation or double or triple and so on. So for all the excitations in the couple cluster hierarchy, that holds. Number of Paulis grows, but all of them are commuting there.
The question, so how does statement that you need singles and doubles relate to the Thouless theorem that says that singles is a generator for all the possible determinants?
Okay. So Thouless theorem essentially tells you that you could go between one Slater determinant to another Slater determinant, right? Using singles.
Yeah. So you're rotating the orbitals, right? So
right.
Any determinant.
But that's that's not enough to generate from a single determinant any state of Hilbert space, right?
Right.
Yes. So
no, I got it.
Yeah. So there are two statements, two tasks in a sense, right? So you want maybe from a single determinant generate all other single determinants, then it's enough to use just the singles. But if you want from a single determinant to generate any state, multi-configuration included, then you need to go beyond. Okay, so just to summarize, what we started with, this unitary coupled cluster theory, it's order independent because it has all these T operators inside the one exponential function. Exact, at least if you don't truncate. That was again shown in 2019 paper numerically. So it should be asterisk exact because I don't think there is an analytic proof that this particular parameterization is exact. Numerically, they've seen that it's usually exact. I was wondering at some point how to maybe actually prove that, but then I realized it's actually not that important because no one can use this form anyway, right? So you would need to do some sort of breakdown of the exponential function, even if it's exact, who cares? Because what we care is something that can be practically done. It's usually have, though, in numerical examples, high accuracy, even in a truncated form, and it's an accessible quantum computer. Now, what has a order dependence and can be used, but then has no algebraic closure is this disentangled version, right? And one needs to, if you do the closure, you start getting this generalized unitary coupled cluster theory. That is somewhat better, I guess, because you have a closure. Now, another way to go, which sort of connects this topic with the adaptive techniques, is that you can try to put just single and doubles, but with repetitions, okay? So repetition helps because we know if you take all the singles and doubles, you start making the commutators, eventually doubles with themselves will give you triples, and then triples with, say, doubles will give you quadruples, triples with triple, and so on. So essentially it will give you the entire set, and that will be enough to eventually represent any unitary if you want, okay? Now, it may be not obvious why the kind of this form is generally exact. I said though the commutators will give you the generators of the higher order, but where are these commutators here, right? So there are no commutators really. We just put the exponential function in different orders. One could be somewhat doubtful whether this is exact, and rightly so. One, I guess, again, somewhat hand-wavy argument because it needs to be somewhat more, I guess, done more rigorously, but at least you could sort of see how the commutators could appear in this form. Turns out that there is a sort of analog of the Trotter formula or Trotter theorem for the commutator of two operators A and B. One can say that this is a limit of say m goes to infinity, and then here it's an exponential function of a divided by square root of m, and then b divided by square root of m, then e to the minus a square root of m, then the b square root of m to the power of m. Right, so sort of that shows that if you put a and b in some orders, eventually you kind of can generate the commutator with a relatively high precision, right? And the commutator of, let's say, single or doubles, two doubles will give you triples. And for that, you need just to put the doubles in this way, right? Of course, in the real cases, m is never infinity. So therefore, it's only approximately we get in the commutator, we get some other stuff. And but I guess the idea here is that with the finite coefficients, we could get arbitrarily close to the commutator eventually, if we put enough of these things, right? That's why sort of in many cases the question of adaptive construction of the exact unitary, if you want exact unitary or any unitary, then you want to specify what is the set of generators that technically, if you do all the commutators and the commutators of commutators, will eventually fill the entire possible Lie algebra, will be essentially complete. And there is I guess, a bit of a ambiguity notation or vocabulary here is that sometimes this set of operators also called generators, and they are indeed generators, but they are generators in the sense of the kind of more like a multiplicative generators, meaning that we want generators from this set to create essentially the generators for the entire algebra, right? So that's why it's ambiguous. The generator for this generative set for the algebra or generators of algebra, because when we talk about generators of algebra, it's usually the things that go into the, well, essentially all the basis vectors, essentially the operators. But here we don't mean all the operators. Say singles and doubles are already enough to generate all others. But in terms of Lie algebra generators, all the generators would be single, double, triple, and so on up to n tuple. Okay, so that's why keep in mind that there is a bit of a people don't use always word generator carefully, and sometimes the generator means it's a minimal set that can eventually get you all the basis vectors of algebra, or it could mean just an entire set of Lie algebra generators. Okay. Yeah.
So one question, in that expression up there,
yeah,
the amplitudes on the right side are different.
Yes. Yes.
So basically you are covering more degrees of freedom to some degree, right? That you're able to represent.
Yeah. Yeah. So the amplitudes could be different, and they are different usually. It's just I guess if you could rewrite this expression in terms of just as exponential product of all the generators of Lie algebra, and then every generator will come only once, and then there will be unique set of amplitudes. But here we repeat this, guys, and but the amplitudes are different.
Okay.
All right, so to reduce the number of exponents, so we usually symmetrize. But that increases the cost for the circuit depth, because usually if you want to have a symmetry adapted generators, then you need to take a linear combination, like in case of, as we saw for the, say, fermionic ones, they can commute with the number of electrons. And then in order to, if you write them in terms of Paulis, there are multiple Paulis that are coming out, right? Okay, so, and that kind of brings me to the adaptive state preparation, but we could do probably a break.
Shall we take to 15, 30?
Sure. And if you get them. Okay, so let's continue. And now the adaptive techniques, which effectively don't use maybe this exponential parameterization of polynomial approximation, but essentially they don't use the fixed ansatz for the unitary transformation. Rather, they just keep adding the transformations based on some cost function that is in VQE is energy usually. Yeah. So let's see. The ansatz that my group developed, and it was I guess one of the first physically motivated ansatzes. Before our work, it was mostly IBM that did this hardware efficient ansatz with the gates that they try to change the order and positions based on, well, and the gates were chosen based on the architecture of the machine that they're using. But we decided, okay, so can we really start with the operators and then maybe figure out which operators, which entanglers we need to put in order to go beyond the mean field description, single or qubit rotations. And that's how the qubit couple cluster theory was created. Essentially, if you'd like to add these Pauli products in the ansatz to build the, by analogy, we call it couple cluster theory, only in the qubit space. And the problem right away is that there are so many potential Pauli products, 4 to the n. So someone needs to figure out how to really navigate in the space of multi-qubit entanglers. Even for lithium H and minimal basis, it's like a lot of Pauli products. And what we essentially here is just a geometric representation. We are working with SU2, the exponential, and trying to figure out now what directions to go. And this is a lot like probably navigating in the simpler problem on Earth. If your energy is just height with respect to the maybe sea level, and if you want to know what's the highest point on Earth, this problem, where to go to find that highest point, one can still use some sort of a gradient, right, information. And the sea level, one can think of it as a mean field energy or Hartree-Fock energy. And then when you add extra entanglers, well, that's an extra direction which you can go. And technically, you wanna figure out, okay, which direction will give you the largest contribution to the energy, right? You will reduce the energy. And this is the delta that you can calculate with respect to the mean field energy for a particular Pauli product for a particular direction. Now, if you take the gradient, essentially derivative at 0 angle, then the expression becomes relatively simple. All you need is just estimate the expectation value of the commutator, right? So, and it turns out that it's not that hard, even though there is exponentially many Pauli products that one can test. It turns out that structure of the Hamiltonian allows you to, and the structure also of the state that you're calculating, allows you to really find the classes of Paulis that will have non-zero gradients. Okay, and so that I want to explain a little bit more, because that little bit of the, oops, we disconnected. Okay, so people online also. Great. Okay, we're back. Sorry for this disruption. Okay, so how do we find where do these classes come from? One thing to realize is, okay, for the Hamiltonian written in a qubit space, let's consider this situation. There will always be two parts. One is the part that contains linear, well, like it's essentially linear combination of Pauli products, right? Always. But these Pauli products can be separated in two groups. One group is, let me call it the group of the Eisen part. So these large Z's, they are products of for individual, I guess, qubits. They contain only Z terms and identities. So there is no X or Y in this large Z products, right? Plus non-Eisen part, non-Eisen part. So that is the rest essentially. It contains the other Pauli products that could have X, Y's, and so on. So why this separation is convenient? Because if we think about the QMF, qubit mean field theory state, which is we call it collinear, or essentially another way to say it's like equivalent to Hartree-Fock, meaning that all the occupations either the spins are up or down essentially, right? Or essentially you have either zeros or ones everywhere. So it's a single product state with only zeros and ones. Right? So that's what Hartree-Fock is in the qubit representation. So it turns out that if you take the expectation value of the Hamiltonian with such state, product state, so here it's a 0, 1. Oh, just for example, like I guess 0, 0, 1, 1, 1 state. And then there will be Eisen part plus non-Eisen part. And again, the same state. So this is a expectation value of H in a product state case. So in such situation, it's easy to see that this will be just Eisen part expectation value. And there will be nothing on non-Eisen part. Why? Because if you consider, let's say, anything that contains X with the product state, this is the simplest example, single qubit X, right? So this gives you 0, because what X does, it flips 0 to 1 and 1 to 0, and they are orthogonal. So anything that contains X or Y on the product state will be just 0, okay? And that's for the Hamiltonian. Now, what we here is interested is the matrix element of the commutator, not the Hamiltonian, but the commutator. But it turns out that it's not very different, because the commutator of P with H, what it is, we know that this P may not be the one that we have in H, but we all know that this P commutation of P with the P's in H, this is kind of the expression, sum over n's, right? So this will be giving us the commutators, and the commutators could only be either 0, the P commutes with the P's that in H, or non-zero, which is the anti-commute, and the anti-commutation results in the P times Pn as a result of the commutator, right? So we will have products like this, which are Pauli products themselves, right? So we could say that P prime, because products of Pauli products is Pauli products again. So eventually we end up with expectation value of these new Pauli products, Cn's, sum over n, okay? And they only will be non-zero from the parts where P n prime, they are essentially Z n's, right? So only the Eisen part of essentially this commutator will contribute and be non-zero, right? So because we can establish what Pauli products in H with a particular Pauli product that we're considering will give us only these. And that's a simple sort of algebra because the general H term will have some letters like some essentially sigma 1, sigma 2, sigma 3, and so on, sigma n. And then when the Pauli comes, so it will have its own sigmas, sigma n's. And in order, when we do the commutator, in order to have, we know, first of all, whether that will commute or not, based on the even or odd differences in the letters. This is Pn from H. And this is P that we are considering, right? So we could always say, all right, so this P is not worth even considering because it commutes maybe with all the Hamiltonian elements. Or we can say, all right, so it won't commute with a certain number of elements, and it's still not worth considering because when it doesn't commute with them, it will produce something that will contain not only these, but x and y's, and then there will be no contribution, right? So we could do all that analysis based on the simple qubit considerations and analyze that, okay, for a particular part of H, we could have a certain piece that will generate non-zero gradient contributions because these commutators will generate eigenforms when we do commutation. Okay, so that's the idea how we sort of figure out what Pauli products should we include so that we have non-zero contribution in the gradient, and which ones will have larger gradients. Okay, so that's just based on the simple algebra of what gives us non-zero contributions to the on a product state. All right, so of course, if this only would be done once, we are done. But usually, what happens is we figure out like what Pauli products is worth introducing, and once we introduce them, then we have a state that is now not a Hartree-Fock state, but rather a state where we introduce some of these Pauli products with a high gradient, right? And now we got a state that is a larger state, and it's also entangled state. So this consideration with a single product state will not work anymore, right? So we will not be able to just follow through, and somehow we would need to kind of figure out on the next step what Pauli products will contribute to the gradient now based on the new state, right? That is not any more simple. Instead of considering more complicated states, what is done in the qubit coupled cluster algorithm, we put these selected entanglers not on the state, but on the Hamiltonian, okay? And so this is always can be done because we, in expectation value, always have a freedom to put unitary either on the state or on the operator, right? In this case, we put it on operator to be able to analyze now with the state, still simple state, what will be the next set of Pauli products that give good gradients. So instead of doing Hartree-Fock, and now this is the first step unitary, what we do is we take the Hamiltonian and dress it with essentially the exponential transformations that are coming from the, let's say we selected the P1 as something that lowers the energy the most, right? And then we obtain transformed Hamiltonian. And for that transformed Hamiltonian, now we can ask again, what would be the next P2, that will lower energy even further, right? And that P2 will be applied on modified H1. And here will be I theta 2 P2 on the Hartree-Fock state. Okay, so again, we reduce the problem to the one that we had before, right? So we have now the product state. We need to decide what is the best P2 to use, but the Hamiltonian is different. It's now the modified Hamiltonian. The only problem with that approach is the modification of the Hamiltonian. We know in general that if you apply unitary to the operator, the general expression is given by this Baker-Campbell-Hausdorff expression that has it's like infinite summation. It's like a version of the Taylor series you could think of, right? So if you have a case of a unitary that is with a generator that is of kind of general, in the general sense, right? So then we know that this will result into a sequence like this, plus G, GH divided by 2 plus and so on, right? And yeah, so that would be not possible for G that is of the general kind. But in our case, the generator is a Pauli product, and we know that the P squared is 1, which means that our exponential function has only few terms, like just 2 terms really. And therefore, this expression has a finite form with just 3 terms. One is the Hamiltonian itself, then commutator, and something that comes from the double commutator. And so we could do that also after optimizing the amplitudes. Some of these amplitudes are small, right? And even though with each step, the number of terms in the dressed Hamiltonian grows exponentially with the number of steps. But we could trim those some of the terms that appear with the small coefficients. And practically, we found that it's more like 1.5. The growth factor is 1.5 into the power of number of steps, because it's some of the terms we could just remove without losing accuracy, right? Instead of being 3 to the power of n, where 3 comes from the number of terms that we get out of each dressing with Pauli's, we get somewhat a smaller base for the exponential function. Okay, it's still exponential, and so eventually we need to stop this process. But as in general, the idea is that you reach accuracy sooner than you run out of resources, right? And so, yeah, so this is done in this form where unitary is constructed as a product of these Paulis that are essentially obtained using this way. And if one would like to avoid this consideration, which we do completely classically, one can try to analyze gradients on a quantum computer, right? So this is something we'll discuss after considering this schemes with the adaptive addition of the various generators, because indeed, if you want to use any adaptive scheme, you will need to figure out how do you obtain this gradients of energy on a quantum computer. And there are ways to do it. It's just usually after, well, they are quite expensive, right? So this is no one wants to talk about. And in practical calculations, in many cases, people just don't do VQE all the way from the beginning to the end. They instead do the optimization on a classical computer and just put the kind of circuit that represents the function on a quantum computer and do one shot of energy estimation, right? Because otherwise they would need to do the optimization of these amplitudes, and that is requiring doing the gradients, right? All right, so these are some results again obtained on the classical computer, just to see that it works and works better than the mean field theory approach, QMF, with the symmetry constraint or without. This is a constrained result answer. Then this is a symmetry broken solution. But if you add, in this case, I believe just very few 7 entanglers selected based on this energy gradient, you could obtain a result that is numerically exact in this small problem like lithium H. But this is again not a very difficult problem because it's only a single bond is broken, and the method like couple cluster theory, single and double, gets it also exactly, essentially. Right, so CCSD is exact. Now, a little bit harder problem, water molecule where we stretch 2 bonds. Now, CCSD is not exact, and actually the blue is exact. CCSD kind of dives below because it's not variational. Again, mean field theory is way above. And here we already need 50, roughly, entanglers in order to get to the chemical accuracy in a water problem. So it's growing, but we still can do it. And then this is just a comparison between number, if we turn everything that we obtain in order to generate our unitaries in QCC into like a quantum circuit, and see how many 2-qubit gates we need compared to, let's say, 2-qubit gate count for the unitary couple cluster theory. If you put disentangled version, if you put all the singles and doubles only once, right? So then in the QCC version with generators which are Pauli products instead of fermionic ones, right? So we have for these 3 systems significantly smaller number of 2-qubit gates. And people usually these days count 2-qubit gates because that's the limiting factor. You cannot, on the current quantum computers, do more than like maybe 100 or so, because the error accumulates. Well, every time you do 2-qubit gate, I think you kind of get some potential error, and after hundreds of those, you would generate the answer that you want with a probability of 30% or less, unless you start doing some error mitigation. You would need to, stop at less than 100. But these numbers, as you can see, we still cannot do water molecule on real machines because it requires definitely more than 100 2-qubit gates. Maybe lithium H is something that can be done, but again, as I said, it's not a challenging problem. All right, so another adaptive scheme that came out after QCC and became very popular, as it's conceptually very sort of straightforward. And this scheme works with, starts with a fermionic ansatz, with essentially creating the operational pool of generators. So what I before called kappas, they call here taus. Essentially, this taus that they're using, this is excitations and de-excitations. Let me just write carefully. P, Q, tau is essentially the A dagger Q, A, P, minus here the conjugate part, right? And if you have 2 subscripts, superscripts, that's a double excitation, de-excitation, right? So they generated this pool of singles and doubles. And what they do, they start with Hartree-Fock Then they analyze energy gradients, the same expression as we have. It's just because their generators anti-Hermitian, they don't need I in front. Our generators was they're powerless, that's why there was I. But other than that, you just calculate the expectation value of these commutators. Now, what you do then, you select which of these gradient is the highest. There's a polynomial number of operators, so you don't, you assume that this is all doable. But to say from the beginning, like I don't think this scheme is really used on the real machine because you won't be able to run this on anything but hydrogen, maybe case. But still conceptually it's doable. Polynomial number of expectation values need to be calculated. And if you found that all of them are zero, then you're converged. If not, then you add in the one with the highest gradient to your wave function and start kind of optimizing the amplitude. Now to do the amplitude optimization, I guess you optimize the parameters based on some calculation of the gradients of energy with respect to parameter. And then once you optimize the parameter of the generator that you included, you do it again and so on. So you every time of this loop, you add one generator into your unitary circuit and recalculate the gradients. Presumably, you calculate all that on a quantum computer. But again, as I said, I don't think anyone has done that. And in this work, I think they only show simulations. Okay, if you look and data presented, it's only simulations. So that was, I believe, 2019 when this scheme came out, Nature Communications, and very quickly people realized that okay, this is too expensive because every fermionic generator, I guess the singles will just generate 2 Pauli products, but the doubles already generate 8, right? Because the formula is 2 to the 2n minus 1. So you quickly start, 8 is quite big number of Pauli products. And so then the same group came up with a so-called qubit adapt VQE, where they already figured out, okay, well, maybe going with the fermionic generators is not the best way to go, but instead, let's figure out the minimal pool of entanglers. And by the minimal pool of entanglers, it's already been mentioned, we take the sigma, like a single Pauli operators, sigma q's, for all the qubits, and we combine that with nearest neighbor doubles. So it's sigma q I, sigma q prime I plus 1. So nearest neighbor allows you to, if you do commutators and the commutators of commutators, eventually get everything in the like a 4n minus 1 set of all Pauli products. But because it's nearest neighbor only, this scales linearly, and this one scales linearly. So overall, they have a linear number of generators in this pool that they then use repetitively. All right, and as you could see, they here thought for 3 systems. The upper panels are for the number of iterations that needed to converge. This the accuracy is on the y-axis, right? And they compare qubit adapt with the adapt technique, and As you can see, the convergence is slower with the qubit case because you are using the operators that break symmetries, and they just cheap, right? But then the number of CNOTs, which is 2 qubit gates, is way smaller in the case of qubit adapt, right? So that's what they were after. Okay.
And they test on these linear systems.
Right. So linear system. Okay. So the
common isn't it kind of
hard?
No, less hard than.
Probably, yeah. Less hard.
Like you know,
right.
You show the linear scaling of linear systems, then
right.
It's kind of obvious.
Right. But I guess the kind of argument for the linear systems, like hydrogen chains, is that they potentially can stretch, right, the nuclear distance between the. So it's essentially equivalent to breaking multiple bonds at the same time, right? Which simulates the strongly correlated systems. But you're right that you could also make, let's say, 4
a ladder,
right, as a another configuration, like a square, for example, and stretch all at the same time. That's a harder case. Or pyramid, or some sort of, there are some 3D, 2D configurations, and they're usually harder. The linear ones are the easiest because the electrons don't interact too much there.
When they're far away.
Far away, yes, right. But it's also minimal basis, so it's just a proof of concept in a sense. One great thing about this work, indeed, they start doing this minimal pool, which is linear and kind of nice. But then if you go too simple, I think you could see that the convergence is not so great, and it's just the gradients of these elements. They are not big, and so it's you could even end up in some local minima probably. And
the I was labeled what?
That's for qubit, and this is for XYZ
component.
Okay, component. Okay, so now there is this work that I think you guys also using. It's the idea that all right, to simplify the single double couple cluster theory excitations here, I just remind what the Jordan-Wigner mapping is doing, right? But the idea is that for single excitations and double excitations, in order to make the generators somewhat cheaper in terms of the gates, you remove the Z's that technically don't do any flipping of the qubits. They just there for the phase factor, right? And so this by Crispin Barnes and group in UK. So that's just another simplification that has, I think, claimed some advantage, I guess, on some systems. They compare with the qubit adapt. The plots, though, poorly done, so it's really hard to see. But in some cases, there is almost no advantage. Like if you look at the energy, and this I presume the QEB, that's the qubit excitation. They call qubit excitation is the part with where they remove the Z and leave just the XY part, right? So this qubit excitation versus I guess qubit adapt. So they go more or less.
Qubit adapt is the green one.
The green one, yes. So this is a slow, But I guess the idea is that compared to fermionic one, the convergence is the number of iterations pretty good, right? But the C nodes are better in the case of which I don't have here, but in the paper they did have C nodes, and C nodes are better for the case of this qubit excitation. You could check the paper, right? So, and then there is this work that finds yet another kind of set of minimal pool, which conserve the symmetry. That's the kind of, this is the part of their introduction where they want universality, meaning that if you do all the commutators, you get all the entire algebra. Check. For all these cases, that's true. In previous works as well, right? Then practicality, which they want to minimize the circuit, but still they want to preserve the symmetry at every step. And so to do that, turns out all you need is all the singles, but the singles that are grouped like alpha and beta singles together. So those are the operators that conserve a square. And you need the doubles that do the excitation, the paired excitation, right? So this goes into the, like this, right? So this is IA. So it turns out if you do just these guys, then it's also, they call it disco VQE, and you could look for more. I posted this work in the reading section, so you could look more details there. But effectively, they added yet another constraint of symmetry and try to, again, reduce the cost on the gate side. Okay, just to summarize, I guess adaptive strategies are more efficient in terms of quantum resources. Of course, you add slowly number of gates or new gates, and number of parameters for optimization is not as high as if you put the entire thing, like in the cluster single and double. Generators, so should be from universal set. Most of the works, of course, satisfy, or all the works I've seen satisfy that, and they can then build the SU2N in general. Symmetry can be either conserved or ignored for each step. There are some works, again, as I was saying before, showing that the value of the symmetry, in some cases, probably that's true. But on the other hand, sometimes breaking symmetry helps to converge to energy faster. And then it's nonlinear optimization. So technically, you could have local minima or areas where the gradients are low. So some of these optimization problems are difficult. And especially, people don't talk much about, I guess, these difficulties in quantum chemistry, because most of these optimizations are done on the classical computer, not on the quantum computer, where on a quantum computer, that would be at another level of complexity, because all your energies and gradients, they are noisy, right? So trying to optimize that. And another difficulty is, to calculate energy gradients on quantum computer. And this is something that I want to discuss next. And I guess I'll just start this, and we'll continue next time. So just to understand how the gradients could be formulated, we have this work also put in a section of literature. You could see the details, but it's based on essentially previous works. But what we did here, the idea was, okay, how can we estimate energy gradient? This is energy with respect to amplitude of arbitrary generator. Okay, and if just one do the simple differentiation, everyone can do that, right? So one of the issues here is that if you are differentiating this generator, that you may want to find the gradient with respect to amplitude, right? So it could be between the other unitaries, right? So that it could be in between. And then what happens is the expression technically is this is still unitaries, but then you need to have a commutator of transformed Hamiltonian with the generator, because once you differentiate with respect to tau, the G comes out, but it doesn't commute with the previous or subsequent unitaries, right? And this expectation value is not easy to obtain, because simply you don't have this operator easily computable, since as we were discussing, the Beck-Campbell-Hausdorff expansion of this could be generally large. and then you need a commutator with G, right? So the G got stuck somewhere in the middle. That's not convenient. So it's a problem. And back in 2018, already people found one way to deal with this type of problems is okay, this is just a repetition of the same thing, but in a simple notation where I skip the wave function, right? So we have this gradient written like this, and it turns out that because some generators are simple, in a sense that they have only two eigenvalues, plus minus lambda here, but for Pauli products, we discussed that for Pauli products, the eigenvalues are just plus minus 1. And what this allows you to do is, turns out you could, if your generator has plus minus 1 eigenvalues, then because the exponential function of that generator will be just a cosine theta identity plus I sine theta the generator. From that, you could simply write the generator here as a like an exponential function of the generator, and then minus cosine identity, right? And divided by 1 over I sine, right? So this allows you to introduce back the exponential part, and it turns out that you could just simply write it like this. So, and this is not it's not really the approximate expression or like some finite difference because of this simplification. It is exact, and what makes it essentially exact is that there is some cancellation, as you can see here. We introduce the shift in amplitude from the expectation value of the Hamiltonian here and here, right? And here it's with plus s, and here is with minus s. So what happens then is that all the terms that we don't want, all the terms which we don't want, they just cancel out. And I could just probably, using the time we have, see how this cancellation works out. So if we have, let's say, minus I tau plus s, and let's make, for simplicity, I guess, if we just ignore, let's make tau equal 0 case, so not to carry the tau, minus I s will be with G, H, then I s, G, right? So that's one expectation value, and then minus another expectation value with minus sign, so it's plus I s, G, H, minus I s, G. So the difference of this, we want to obtain this expression right here, right? And because each exponent can be written for generators with plus minus 1 like this, then for this one we'll have 4 terms. First term will be essentially identity H identity with the cosine, I guess with cosine with will be both with pluses here, cosine of s squared, right? So this is the first term. Then we'll have last term, I guess, will be with 2 signs, and since it's I and minus I sine square s, this will be just plus 1, and and then we will have expectation value of G, H, G, right? And then we'll have a cross terms where one is one, it's like a cosine of S with the sine S, and with one will be with I, another will be with minus I. So let's just say it's I identity H G, and will be minus I H G. Oh, sorry. GH. And then in this term, we will have it's actually repetition H cosine square S plus sine square S, expectation value of GHG. And this term will be just with a different sign, minus cosine S sine S here I HG minus I GH. All right, and if we subtract this term from this term, you could see that the common terms here and here, they will cancel, and these two terms will add up if we kind of make a difference between this and this. And then the only thing we need to do is to kind of divide by the coefficients in order to get the expression IHG minus GH, which is a gradient, right? So this is how this rule sort of works, shift rule works. And there is a, I'll stop at this and we'll talk about generalization next time. But one thing to kind of use as analogy is just how do we numerically differentiate functions in the, like on a normal classical computer. You could have a function of x, right? And in order to find the derivative, you take the difference between the value of the function at point x0, let's say, and point x0 plus delta, and then divide the difference by the delta, right? And this is always approximate. It needs to be limit delta goes to 0 to be exact, but it's not like there are some functions f that actually will make this formula exact, right? And we know this, all right? So if f of x is a linear function, then 2 points is enough to get the gradient, which is a if f of x essentially is ax plus b, then for any delta, this formula with a finite difference will be exact. Now, if function is polynomial, like quadratic, then you need more points, but essentially it's also going to be exact. Turns out that in operator language, what makes operators easy is the number of eigenvalues. Okay, so it is like polynomial degree, and it's easy to understand because look at the exponential function. We always work with the exponential functions because we want to code unitaries, and exponential functions can be written as a polynomials. Here it's a linear polynomial of g if the number of eigenvalues in the generator is finite, right? So if it's 2 eigenvalues, then it's linear. If it's 3, then it's quadratic, and so on. So there is a natural analogy between number of eigenvalues in the generator and sort of polynomial degree when you express the exponential function. Okay, that's what makes it doable in this form. Okay, and that's the origin of generalization that we found for, let's say, if your G is not just plus minus 1 or plus minus lambda generator, if it has more, it's richer spectrum, then still this kind of manipulations can be done as long as it's finite, and it's always finite. Okay. All right. That's all for today.
Thank you.